What's up, everybody? Today we're going to talk about very important subject. Okay, today backstepping control. Right? Let me just arrange the colors. Okay, and backstepping control is one of the most prevalent and I guess you can say performance-wise maybe significant control. Okay, and it would be better for us to it would be good for us to get ourselves familiar with that control, I thought. And now this video will be like 3 parts. First we're going to talk about maybe for the basic concepts, and then in second part we're going to simply focus on examples, and then I'm going to talk about how you would program that by using symbolic toolbox of matlab. Okay, and then a summary session, right? Like the summary of the algorithm, or this is a control algorithm, right? This is an algorithm in a way. I mean, so you can use the word algorithm in control as well, is what I'm saying. Okay, so for example, in Hasan Halil's book Nonlinear Systems, 3rd edition, there are 5 very important control algorithms, nonlinear control algorithms are mentioned, and they are: first, sliding mode control, and 2, Lyapunov based, 3, backstepping, 4, passivity based, 5, high gain observers. I mean, it's not control, but yeah, you can use you can construct your own like high gain control too. Okay, all right, let's move on. And backstepping is one of them. We in the previous videos we have talked about SMC, sliding mode control, and in this video we are going to talk about backstepping, and also as a like side bonus, right, Lyapunov based control. And so after this video we will have, I guess we will be done with 3 of the 5 important nonlinear control algorithms. And hopefully in the future we are going to look at the 4 passivity based and 5 high gain observer subjects. Okay, let's move on. Okay, and basic concepts, we are going to talk about basic concepts. Okay, and first of all, let's consider this system. Okay, here there are 2 states, eta and xi, right? Eta and xi, right? And u is our control input. Okay, and maybe let's get that. Okay, so you can see it has some special structure, right? Okay, and this type of structure, like chain structure, okay, chain, like one subsystem, 2 subsystem, right, etc. And in a way it is in decomposed form, and this special structure will help us construct systematically nonlinear control algorithms that we will later name backstepping control. Okay, and this is the block diagram of this nonlinear plant, right? Okay, so the problem is that it can be stated as this, as the following. The problem: design u, of course, state feedback, right? And such that the states, go to 0, right? As time t goes infinity. Okay, so another way of saying that, design u such that, of course, state feedback, closed loop stability is guaranteed. Okay, and choose phi function. This is like first name drop of our video. Phi function, we will define a function called phi. Okay, and let eta xi equals phi of eta, right? Okay, by the way, today it will be really challenging for me because it's all of those Greek letters, right? Yeah, they can get hard sometimes. All right, so let's define this, all right, and such that this given condition is guaranteed. Okay, so first of all, let me just say this. This is the structure, right? Okay. Backstepping control suggests that, hey, start from the end of the IS chain, right? And focus on this subsystem, right? And consider this is a state, but it is an input to that subsystem. Okay? So just focus on this. Just cut that part, right? Just focus on this part. And consider this xi as your input, and eta is the only state that you need to, think about. Okay? And so the problem is that it is a CISO nonlinear control problem at this point. How would you solve that? Right? Design a xi, right? Let me just make in latex xi, eta, phi. Is there any Greek letters? Okay, no. Alright. And design this xi input, okay, such that this system, when I say this system, I mean eta is stable. Eta dynamics stable, right? Okay. So this is the first way of approaching this problem, or this is the first idea of the backstepping control. Okay. So, and by the way, you will need to employ, right, state feedback control, right? So you can just express your xi in phi of eta. Okay? And the problem becomes find phi of eta such that eta dynamics stable or unstable. Okay. So let's focus on this problem, right? And it has only 1 0 and it is at the origin. Okay, yeah, this is a one assumption or one constraint on the phi of eta, the function that we need to, construct or determine actually. Okay. And so, okay, this is what we have, right? And again, instead of xi, we write our control algorithm, okay, phi of eta. Okay, so the problem becomes, what is the condition of phi of eta for the eta dynamics to be stable and asymptotically stable, right? Okay, let's use a Lyapunov function, right? What will the control engineer do? Engineer does in that case, right? He or she would first try to use that, and given that it's a CISO nonlinear, meaning it is not really an extremely complicated problem, right? I mean, there are way complicated problems than this, right? CISO nonlinear control, right? So your first objective or first instinct would be to, okay, let's employ Lyapunov-based control design. Okay, meaning let's construct a Lyapunov function, and it's like a typical quadratic form, and construct its time derivative, right? And let's determine under what condition this time derivative of our Lyapunov function, candidate Lyapunov function, becomes negative for which input, right? This, and the problem at that point becomes an algebraic problem, and it is something that we can handle, right? Compared to the PDEs, right? Partial differential equation type of problems, okay? All right, so Lyapunov function must be positive definite function, okay? There will be two, right, main constraints on that, right, function, okay? And time derivative of Lyapunov function must be negative definite, okay? Just two constraints on that function, v of eta, right? So in a way, now we need to find phi and v, two functions at the same time, right? Simultaneous, right, function determination in a way, okay? So, and since we kind of assume in a way that we know that, let's focus on, we know or we will choose a v, right, we upon a function. Let's focus on the time derivative of that. Okay, and time derivative can be written like this. Okay, and what's eta dot? Eta dot is this, right? Okay, so we are focusing on this problem, right? This is something that we need to focus on right now. Okay, so and this is the constraint, right? Time derivative of the upon a function must be negative definite. Okay, and or you can also write something like this, right? Time derivative of the upon of being less than minus or less than negative definite function, or minus less than minus 1 times a positive definite function of eta, right? Okay, so let's move on. We are not stating, we are only stating obvious things right, so far. Okay, so this is something that we are interested in. Okay, we are going to analyze, right? Okay, let's expand this term, right? And that becomes this. Okay, right? So, and now in a way the problem, you can kind of say that, hey, the problem first was to find a phi of eta, and now we are going to find phi v1 and w. So are we getting somewhere, or are we, making our problem more complicated, right? All right, and so, and the answer is that you are going to see that, but we are not making our problem harder, right? It's going to come to a point where you realize, yeah, now I got it. Okay, so bear with me. By the way, I should have said this in the at the start of the video, but I can guarantee, right? I can guarantee that, right? You are going to learn what backstepping control is. If you watch that video, and at the end of the video, right, after you're done with watching that, if you have like, hey, I don't get what backstepping control is, and I have at least a little bit of control background, so don't watch me again at that point, right? I can clearly say that this video will be my masterpiece, I feel like. Okay, all right, so, and at the end of close to the end, I will straight give the algorithm, necessary algorithm, and we are going to work on the problems, and it will be clear. I can guarantee you it will be clear. Okay, let's move on after that little advertisement, right? So Lyapunov function must satisfy these two constraints. Okay, all right, so we are slowly building on, right? Okay, and step 2, change of variables. All right, this is our problem. So find phi, v, and w. Okay, all functions of eta. All right, so this is the change of variables, right? And at that point things get kind of annoying, I will say, right? If you are trying to learn the subject by using Hasan Halil's Nonlinear Systems 3rd edition book, right? This is the point where you get kind of confused. Okay, but it will be clear. So I'm just explaining, right? This is a introductory explanation, and at the second stage you will learn. It is just an algorithm. Just like Gauss-Newton algorithm, right? Newton-Raphson algorithm typo. It is just an algorithm. Somebody just figured it out, and you kind of see how algorithm works. Okay, and that's all. That's all. Not complicated. Not more complicated than that. Okay, so, and by a simple algebraic manipulation, we get this, right? So this is our problem. This is our original problem. Okay, so instead of writing eta, we write z plus phi. Okay, so this is a how can I say, we are just trying to map our problem. Okay, back on, like, at the start we had xi and eta, right? Okay, so we did some change of variables, right? Like Fourier transform, for example. I mean, like a transform, right? We are just transforming and focusing on transform problem. Okay, all right. And question is that why would you do some transformation? And the answer is because it will make things easier for you, right? And at the end, we are going to see that type of employing that type of transformation will make things easier. Okay, let's continue. And we are mapping our states, right? Eta to eta. Okay. By the way, for the sake of argument, you can just give another name than eta, like eta 1 or something. But yeah, actually that would be pedagogically more correct, I feel like. But this is what most people do, right? So we don't just give another name because eta to eta is an identity type transformation. All right. And xi to not z but z plus phi of eta. And at the end, or let me, but at the end, we have z and eta. Okay. We first had xi and eta, and we did some transformation. Let me say just transformation, right? And now we have xi and eta. Okay, all right. So let's see what happens, right? Okay, and this is our problem right now. Okay, so let's do this algebraic manipulation and kind of isolate z. Okay, right. So nothing wrong with that, right? Okay, and the problem is, what is z dynamics, right? And because we have, as I said, we had xi and eta, we are making a transformation or constructing a transformation, and by which we will have z and eta, meaning we will have z dot some function z and eta dot equals again some function, maybe function 1 and function 2, right? Yeah, we will have that. Okay, we are trying to obtain this, right? Okay, so how would you obtain that? Just, this is our definition of our variable z, right? And just take the time derivative. Okay, this is where we are, right? And again, time derivative of z dot, eta dot, and phi dot. But phi depends on, eta, so you just can't do that directly, and you will write something like this, right? You will write this, by expanding we get this expression. Okay, so far so good, right? Okay, it is like a TV show, right? We're just watching and we're just trying something, and what happens, right, at the end of the season finale, I guess. Okay, and I can guarantee you it will not be, you won't see a plot twist where you get nowhere. You will learn backstepping control. Okay, this is my, alright, advertisement. And okay, we are here, but by using our first problem, right, we know what xi dot is. Just write u. Okay, just substitute u. Okay, for xi. All right, so now at that moment in the new coordinate system that I said, right, the dynamics, when I say in the new coordinate system, the dynamics, when we say the dynamics, we are saying this, right, the dynamics. Okay, z dot equals something, and eta eta dot equals something. Okay, so here we just found that, right? Let's look at the right hand side, right hand side of this equation. It's all eta and z. Again, it's all u. By the way, u, since we will write u in terms of eta and z, so you can think of it as a function of eta and z. So nothing wrong there. And again, eta, again, this term will be dependent on eta. And this term, by the way, that eta dot term will be this really long expression, by the way. Let me just tell you, really long expression. Okay, maybe it would be better for me to, get this. Okay, point across. Eta dot is this, and since this long, really long expression is a function of eta and z, right? This is a function of eta and z, and we know this is a function of eta. So this term is a function of eta and z, and again we will write this with that as a function of, right? You can also, you might as well write eta u of eta and z, right? As a function of eta and z, right? Okay, so this is a function of eta and z, and this term finally is a function of eta and z. So okay, so let's try to arrange the terms. Okay, this is it, right? We just write that in a simpler or compact way. All right, so now to make things easier, let's define a new input signal, v, right? By the way, I don't know about you, but back in high school especially, right, there are some integration factor type of formulas that you need to memorize, right? And I hated when they use u and v as variables, because they kind of look, from far they kind of look similar, right? You could have used, I feel like they could have used little more distinguishable letters. They look similar, right? So that, yeah, I always question that type of stuff, by the way. Okay, always question the education system. All right, let's move on. Therefore, the new dynamics is this. Okay, so the problem becomes this. First, we have some problem P1, and then we change it P2, and then we change it to P3, and then we change it P5, dot, right? And by the way, I'm just writing that arbitrarily, right? Maybe it's P5 or P3, I'm not sure about that. But the point is that if you solve this, you can solve P1, or you can retrieve the solution of P1, right? This is the kind of strategy. All right, so again, this is the block diagram, right? Okay, so now the new problem is as the one given in the block diagram, right? And the second subsystem here, this is the second subsystem, okay, and is asymptotically stable when zero input z signal, this is the input to this subsystem too, okay, when zero input is applied. Okay, and this is like the most important, right, detail. The only reason that we transform that system into this form, that if you can guarantee that when you apply zero input to that system, the dynamics are stable and asymptotically stable, your problem can be solved in a really systematical fashion, right? And we are going to employ that way of solving that. Okay, we will see a pattern is, yeah, the main point. Okay, because this is an important property, right? And you will notice that in the comment. Okay, all of the transformations and the new variable definitions were introduced to make the second subsystem asymptotically stable, and this has consequences, right? Now we can find u input, not you as in person as a person. We can find yeah, I'm going to make a silly joke. Yeah, we all in contour we always try to find you. Yeah, okay. Right. That was silly. Right. The open function in this coordinate frame. Right, okay. And the reason why we were not able to find u in the original coordinates by using the open function approach is that if we did, we would have, yeah, that type of terms. Okay. As a in our control law, yeah, right? And as xi goes, and this is a problematic term, because again, as xi goes to 0, right? Look at this. These terms becomes problematic, meaning they will not converge to 0. Okay. All right, continuing. The new problem, design v such that eta and z goes to 0. Okay, this was a side note, right? Okay, choose the Lyapunov function. Choose the Lyapunov function as this. Okay, right? This is first. We are just trying to solve or obtain a contour algorithm using the first our first way of doing that. What was it? Lyapunov based contour design. Okay. Okay, and but we know that z can be written like this. Okay, and so in a way, our function, our Lyapunov function, is a Lyapunov function of eta and xi. All right, and since we have talked about this subject, what was that? If you transform that problem such that you have this, and what's the property of this system? If the second system such that if you apply 0 input, if eta is guaranteed to be stable, asymptotically stable, that's a important property, right? And due to that property, okay, due to that property, we can write our first Lyapunov function in this form. Right? I mean, it is, you just can't write a function in that form. You cannot do that all the time, right? It is not something that you can just do, right? But if you can do that, if you can decompose your function, right, it will have important impact on your problem, right? Okay, so this must be positive definite function. Okay, we know that, right? It's the Lyapunov function, and the first part must be positive definite function. Okay, just let me say that. Let me maybe make it clear. This is our Lyapunov function. And this must be positive definite, and as a result of that, this must be positive definite, and this is already positive definite. By the way, we could have chosen something like this, by the way, right? And even writing that is an assumption, by the way. So we could have written this, and that would be more general. However, the reason why people do that type of without loss of generalization type of claims, because otherwise it would be I mean, you are going to see that, by the way, in the problem session, right? The expressions get incredibly long, right? Okay, you can even compare at this moment. It is impossible, by the way. Okay, just, and again, important, my small rants, I'm going to, okay, claim something. If someone is talking about backstepping control, right, and in the same paragraphs or something, right, statement, if that person doesn't mention matlab or mathematica, it doesn't matter, but symbolic toolbox, or using symbolic toolboxes to obtain a control law, right, be skeptical of that person. I'm just saying, okay, all right, just, this is my opinion, right? Okay, and all right, let's move on. Yeah, this must be positive definite and this must be negative definite function. Okay, you would expect that, right? Okay, let's again make it more annoyingly clear, right? This must be positive definite and time derivative must be negative definite. Okay, okay, and as a result of that, this must be positive definite and time derivative of that function must be negative definite, right? Okay, and this is already positive definite, but z dot, meaning this is like if we call it v2 of z, right, and v2 dot is this, right, and this term must be negative definite. Okay, just, this is right, obvious stuff, right? Okay, so okay, we are just stating obvious things here, right? Take the time derivative of that expression v2. Okay, here for example, once again, this is v2 and v2 is composed of v1x and this quadratic z term. Okay, okay, right, v1x, we just substitute that and this quadratic expression. Okay, so let's just distribute this time derivative and we will obtain this and this term. Okay, so let's expand that, right? Let's expand this, and what is that? Let's look at our block diagram. Yeah, this is it, right? Okay, this is it, our original expression. Okay, just doing some algebraic manipulations. By the way, they are all algebraic manipulations and simple stuff. Okay, so here the important manipulation. You see this z term, just get that out of that parenthesis that you see, that we will call eta parenthesis, right? Okay, this expression and this expression. Okay, so we did, it looked like we did nothing, but it will have consequences. It will, right, make things easier for us. Okay, so the problem is that just, okay, what's the problem at this moment? Now the problem, for example, always in contour, we have some p1, problem 1, and then we transform it and we obtain p2 and dot dot dot, and we obtain p10 or something, and maybe we are at p10 stage, right? And the issue is that if you solve p10, you can easily recover the solution of p1. Okay, this is the general idea. Okay, and p10 we transform such that p10 is easier to solve. Okay, so let's, once again, I am a really ardent proponent of that idea. You need to write your problem statements. Okay, so at this moment, What is the problem statement? Problem statement is that find v1x of eta such that it is positive. Okay. And find phi of eta. Okay. Okay. And such that, again, such that this inequality, let's call it inequality 1, holds. Okay. So this is the problem definition. Okay. So if you, for example, give that problem to a mathematician, I don't know which field would be more interested in that problem. I don't know if algebra or some PD guys, right? Or some PD people. And they will, hey, yeah, okay, that is something that I need to solve. They would be like that. Okay. All right. It's not your job, you little control engineer. It is our job at this moment. Okay. They would have that type of attitude. Okay. So let's write this once again, right? Okay. And I forget that. I'm sorry. I forget that. You need to write v instead of, you need to substitute v for z dot, right? Okay. And also find v of eta and z. Okay. So you need to find 1, 2, and 3. You need to find 3 functions, okay, such that this is condition 1 and this is condition 2. And again, v is a function of eta and z. Okay. Okay. This is the problem definition. Okay. So now I am going to change the problem definition a little bit more. Okay. And so this expression must be negative. Okay. Negative definite function. Okay. Can we say this expression needs to be negative definite and this expression needs to be negative definite. Can we say that? Yeah, we can say that, and that is called sufficient condition, right? I mean, just it is a manipulation sign, but not that this implies this. It doesn't mean that. Okay, so it is not implies sign. Okay, this is, hey, I just manipulated something and I get this sign. Okay, and mathematically it is not correct. I agree. Okay, and if we were to be mathematically correct, we would write this, because this conditions, or this set of conditions implies this condition. Okay, and as you know, sufficient conditions, they are harder to satisfy, but on the plus side they would make things easier. Okay, so this is our constraints. We just change this constraint. Let's say we need to find, find p1 of x and p2 of x, and there will be some constraint 1, constraint 2, right? And this is our problem 1, but we also have, and due to some reasons this is hard, right? But we can change the problem. Maybe constraint 1 star and constraint 2 star and constraint 3 star. Okay. Right? New constraints. But these constraints imply these constraints. Okay? But they are harder to, satisfy. So this set, right, is smaller than this set. Okay? This is solution, right? This is solution set. And this is, let's say, this is set 1 and this is set 2. So this is set 1. And this is set 2. But this is easier to solve. This problem is easier to solve. Is general idea. Okay. Okay, I went ready. Okay. Tangent there. So what is, yeah, so v1x of eta must satisfy these two constraints. Okay. And we are not done right now. For example, let's look at that constraint, right? And v1x must satisfy these constraints. Okay, right. Being positive definite, right? And this. Okay, and we can write this constraint in that form, right? As a, sufficient condition where wx of eta is a positive definite function of eta. Okay, right. We are slowly building on, okay, and yeah, that implies this actually. Okay, right, given this is a positive definite function. Okay, so let us recall the v1 of eta function that we have constructed to determine okay, phi of eta function, determine phi of eta function here, right? This is the first v1 of eta. Okay, and at that moment you are like, what v1 of eta? Okay, we are at the page 3. Okay, so let's go back. And yeah, this v1. Okay, choose xi as phi of eta such that there exists v1 eta positive and time derivative is negative. Okay, the v1 of eta that we needed, or that we used to, to construct phi of eta. Okay, so let's go to page 3. Okay, here, yeah, these were the constraints on that v1 of eta. Okay, and we are like, hey, wait a sec. These two constraints, or rather these two problems, they look really similar, right? Okay, and therefore it's almost like v1 of eta and v1x of eta, they are the same, or they can be selected as same. Okay, all right, so that's the good news, right? Okay, and let us go back to Lyapunov function constraints to design v. Okay, these are the constraints. Okay, our origin, I guess, in the previous constraints. Okay, but by remembering that, hey, we have dealt with this v1 to find phi of eta before, right? Okay, so we can just focus on that problem. Okay, that's great. So the constraint 2, and this is constraint 2, can be changed by another constraint. Okay, all right, this is constraint 2, right? And again, it's negativity constraint, so we can just say, hey, rather than imposing the negativity constraint, that just because we are trying to find v, right? Just equate that expression to a negative function, because we are going to determine what v is. Okay. 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 A sec. Okay. So let me look at that. Right, there's no problem. All right. So this actually, I'm sorry, wait a sec. Yeah. This implies this. Okay. And then find v. Right? Okay. So first of all, we are at a really good point to state the following. Again, we have some original problem and we transformed it and we changed some variables, right? We again transformed it, we obtain another control problem, etc. And finally, this is our problem that we need to solve, and the point is that if we can solve that, we can retrieve the solution of the original problem. Okay. And first of all, what do you see? We see that the problem statement is this: find phi of eta, v1 of eta, w of eta, and v, this v, okay, this v of eta and z. Okay, so 1, 2, 3, 4 function. Find simultaneously, right? Simultaneously find 4 functions, these 4 functions, such that constraint 1, v1 of eta is positive. Okay, this is constraint 1. And w of eta is positive. Okay, this is constraint 2. Okay, and this is third constraint. Okay, and this is fourth constraint. So the problem is this. And we transform our original problem to that. Okay. And you may say that, hey, but it's a partial differential equation. I mean, isn't it a hard problem? And the answer is yes, but we can make it. We can, again, by following some easy steps, some assumptions, and also imposing some sufficient conditions rather than the original conditions that we have right now. Okay. For example, we can just select this term, and we can just select that and find this, right? Okay, this is not hard stuff. Okay, and when we find that, we know that right? So step by step we can solve that, and we can just choose. We can, again, let me just restate that. Okay, we can use a typical Lyapunov 1 over 2 eta square type of Lyapunov function. Okay, this is it. First of all, as v1, right? Okay, and then we can just make this as eta dot or something, eta square or something. We can just choose that and find phi. Okay, we can do that. It's not hard. We can do that. This is an typical, by the way, we can make it equal, right? We can make it equal. Okay. And again we can make it equal to minus k, and k is a positive number, or maybe just minus z square. And then, and since we know that, and we also know z, right? It's z, right? We can solve for v of eta z. Okay. So the problem can be solved algebraically and systematically. Okay. And this is the advantage of backstepping control. Solving for v yields, again, this, right? And I'm looking at this. Yeah, just we can factor out z. Okay. And we can solve for v, or we can express v. This k is just a positive number. Okay, just positive real number, just design parameter or something. Okay, we can write explicitly v, our control algorithm of the transformed problem. Okay, therefore we can write this. Okay, and again this is a positive number and k is a positive, so this is a negative function, negative definite function of eta and z, and time derivative of v2 of eta z being negative definite is shown to be, right, the case, and which indicates the stability of the system. Okay, so we just solve our problem, right, in that coordinate frame. Okay, so, and we know, by the way, what v is. We just stated that way, right? We can just recover u. Now we are going to just recover u. Okay, again a simple algebraic manipulation. Okay, let's expand this phi dot expression. Okay, and here there's eta dot, and what's eta dot? And now we write that in the original problem, right? Eta dot in the original problem. Okay, because remember, the original problem is that u, we have u of xi eta and eta, and we have this in the original problem. Okay, and we change that to z and eta and z and eta. Okay, we change that, right? And now we change the problem, and we determine the structure of v, and then now we are going to recover u. Okay, so we are going to write u as a function of xi and eta. Okay, and here what is this? I guess we are, wait a sec, what was that? I'm confused right now. Okay, yeah, we just substitute v. Yeah, where is v? Yeah, v is here. Okay, we just did that substitution, right? kz here, and v and g. Okay, this expression. Okay, so there is no problem here. And again, at this stage we need to find u as a function of xi and eta. Xi and eta. Okay, this is a function of eta, 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 eta and xi, but this is z, right? So we need to just recover that. To recover this contour algorithm, we will just write this, okay, because this is the first, I guess, equality that we have written at the start of the video, right? Okay, or manipulations. So this is, let's find, do a final check. This is a function of eta, right? This is some number, okay? Again, xi, eta, and xi. Okay, so this is a function of xi and eta, and we have guaranteed by using these equalities, manipulations, right, that if you use that contour algorithm, right, you can guarantee stability. Okay. Okay, now this is the part where I try to kind of get or pretend that I know math. Okay. So find phi. So what I'm trying to say here is that the backstepping contour or the contour problem can be stated in this fashion as this: find phi v1 w, right, such that v1 is positive, w is positive, this equality holds, right? Yeah, this is the first part, and then you will find, if you find that, for example, what you need here, this is just a number, okay, don't worry about it. You need to find phi, okay, that's right, what we need to find to determine our contour algorithm. Phi of eta, okay, here we know this, and we know, or we need to know, v1 of eta. Okay, so if you can find that, right, and you need to find such that these conditions are satisfied, right, you are done with your problem. Okay, all right, this is the general idea. This is the general problem definition, but easier version can be obtained by assuming, just assume this, right? Here you need to find these two expressions, right? Okay, and by the way, also there is a hidden w of eta, right, variable that we need to find, right? Okay, you need to find these three terms, but just backstepping contour, I guess it is part of backstepping. I guess you can just assume assume v1 of eta as this, as a typical 1/2 eta square, typical Lyapunov quadratic term. Okay, and if you have that eta dot, meaning this is v dot, v1 dot, right, v1 dot, this is it. Okay, you can write that. Okay, and again, by assuming, you can just assume this. Again, you can just assume this, right? And at that moment, you have this, and you just can solve algebraically. You can just determine phi of eta. Okay, then solve. Okay, this is assume. Assume, maybe choose them, and then solve. Okay, so by using algebraic operations, right, we were able to determine our contour algorithm. or construct our control algorithm. Okay, and again, this nonlinear control algorithm, and as you know, it is not easy, but we get there through easy steps. Okay, so this is problem one. Okay, I hope I can make things easier, and I can just add like chapters in this YouTube video. Okay, and this problem one comes from Hasan Halil's Nonlinear Systems 3rd edition, example 14.9. Okay, and but I can guarantee you my solution is way more systematic. Okay, because this person is extremely smart, and in my okay, I'm going to say really interesting idea, state my idea. For example, you want to learn physics, right? Okay, is it possible, really possible for you to learn physics from Einstein, or somebody who knows physics and his or her IQ is really close to you? Which strategy you would prefer, right? I would prefer the latter one. I wouldn't prefer, hey, I want to learn physics from Einstein, because I'm not, I know that, or I can confess that I am not at that level, right? Okay, so it is, so I guess what I'm saying is don't study contour from this book, just watch my videos, which is, of course, I'm not saying that, but yeah, I'm just trying to make a little interesting point. Okay, and okay, this is the problem here. The states are x1, x1, x2, and x3. Okay, so the problem is that find u such that the closure is asymptotically stable. But let's look at this, by the way. U is x1 dot. Okay, I'm sorry, x3 dot. Here, x3 dot. And the output of that is x3. And x3 is an input of the x2 dot subsystem here. Okay, and the output of that second subsystem is x2, and x2 is an input of the third system, which is x1 dynamics, and the output of that is x1. So we can only employ, or this is where backstepping control, I guess you can kind of manipulate your original problem, but these type of plans, where are the plans, where are the times where backstepping control algorithm shines. Okay, so if you can express your planned nonlinear dynamical system in this, as in that type of, you know, chained system, okay, your first instinct should be, hey, let's use backstepping control. Okay, all right, so all right, this is, I just written the problem. Okay, so first manipulation, by the way, let's look at this beautiful tables, right? Really tidy. Okay, and just write x1 as phi1 plus z2. Okay, don't ask why. Just do this, all right? Because I can guarantee you this is an algorithm that will make things easier, right? And you can, at the end, you can just check using simulink or something, right? And just take the time derivative, right? Take the time derivative. You have this, okay, right? But if you think that you can get confused, you always write phi1 as a function of x1. Okay, just this is important. Okay, so and just arrange that as z2 dot equals dot dot dot. Okay, and just substitute this x2 term. Okay, substitute that. And by the way, this is just using this and this. right? We expressed z2 dynamics in that form. Okay, and now this is our problem. Okay, so the variables are x1, x2, x3, and now the variables are x1, x1. Just don't say phi1 because phi1 is a function of x1, right? z2, z2, and x3, right? Again, phi1 dot is also a function of x1 and z2, right? Okay, so which is this is in a way a type of coordinate change, right? Okay, so let's write that this is the same as this, right? Okay, we did nothing there. And again, as in the previous case, we want to transform our problem from x1 z2 x3 to x1 z2 z2 and z3. If you also name z1, if you also rename, right, name x1 as z1, that would be, yeah, that would look better, right? But they don't do that because x1 to z1 would be an identity map. Okay, identity transformation. Okay, so these steps same as given in that manipulations. Okay, and as a result of that, we obtain that again our variables are x1, z2, z3. Okay, so the problem becomes find u, and u, right, u is a function of x1, z2, and z3. Okay, okay, here this is our problem, new problem, and use this Lyapunov function. And the reason why we did that coordinate change such that we went from x1, x2, x3 dynamics to x1, z2, z3 dynamics is because we know that due to the structure of the original plant, right, we could write our Lyapunov function as composed of the terms that are individually dependent on the states. Okay, because you cannot do that. This is not something you can do, right? For you to be able to do that, your system might have some special structure, and this chain structure is what allowed us to do that. Okay, to write our original Lyapunov as a composition of smaller parts. Okay, by choosing, again, we are going to choose these like obvious, right, or simplest quadratic Lyapunov terms. Okay, here a note, more sophisticated functions can also be chosen. Okay, right, so now a bit of algebraic manipulations. We know that since all of these terms are positive definite, since we know that by construction, and we also need to find u, right? We will find u such that this is negative definite. Okay, let's expand our original v. Okay, using this, right? Okay, using this, and let's distribute the derivation. Okay, and let's substitute, right, the corresponding terms. And here, this is what we have. Okay, we kind of write the problem. Okay, so we are just trying to algebraically manipulate that expression, and by expanding we get this, right? And this must be negative definite. Okay, and now at that moment you start to do something actually easy, right? You look at your parentheses, right? You will, from this you will obtain this, okay? From this inequality you will obtain this inequality. If there is any zi term in first parenthesis, carry them to their corresponding parentheses by arranging the terms, and I will explain what that means. Okay, arrange left hand side such that there is only x1. By the way, this is right hand side and this is left hand side. By the way, let me just show you, right? Okay, from here to here we need to go. Okay, and arrange left hand side such that there is only x1 and phi1 terms in term 1. Yeah, okay, so this is x1, this is x1, this is phi1, but this is z2. So, and by looking at the structure of that expression, we can say that this is a terrible typo, z2 and z3. Okay, I hope this error won't propagate. And yeah, we need to get this z2 here. Okay, you just put, yeah, not hard, right? Okay, it doesn't propagate. Okay, that's, I'm glad. And okay, this is the first rule, right? And arrange left hand side such that there is not any z3 terms in term 2. Okay, let's look at this. Phi 2, okay, it can be, and phi 1 dot, okay, it can be in that parenthesis, right? But there is z3. So we need to get this to that. Okay, all right, this is just algorithm, right? Don't, I mean, in the introduction stage I can't explain the logic behind that, behind those manipulations, so you don't get to ask why, because in the first stage I can't explain that. Okay, and okay, this is where we started, right? Here there is z2. Let's get this to here, or rather let's get this to here. Okay, so this and this identical, and we need to put x1 because this is x1, right? Okay, and is in additionally here there is z3, and we need to get this z3 to here. Simple algebraic manipulation by just putting z2 here. Okay, just algebraic manipulations, by the way. I'm not doing anything more than that. So now this is the problem that you need to worry about. Okay, so find phi 1, phi sub 1 such that this term is this. You could have chosen minus x1, but this term is helping you, right? So do not cancel the terms that helps you, right? That are helping you, right? Okay, so but this is not helping you, right? This makes things unstable. This term you need to cancel, right? Okay, so that's why I just written this term instead of minus x1. Okay, so that's a long explanation. Okay, so this is the equation. Just solve for phi 1. Again, this is function of x1. Okay, now let us focus on the term 2. Okay, and this is term 2, right? Okay, so this is our original problem, right? Here we just equated minus x1 type of minus x1 cube, right? Type of thing, right? And if we can make this expression minus z2 and this expression minus z3, right? It would be great. Okay, can we do that? Yes, we can, because phi 1 is something that we choose, right? Phi 2 as well, right? And then we will find u. Okay, the control root is a function of x1, z2 and z3, and then we will resubstitute. Okay, all right, here okay, a sec. Right, we want to have this is what we have, but we want to have this. How can we have this? By manipulating phi 1 or finding, right? Solving for phi 1 and then phi 2 and then u of x1, z1, z2. Okay, so we determine phi 1 here, right? So we want this here because we want this to be, minus z2. Okay, and we know what phi 1 dot is, and we need to find phi 2. Okay, here, right, just expand phi 1 dot. Okay, and here this is phi 1 because we found that. Okay, or rather this. Okay, it kind of gets really messy, but I'm sorry about that. Okay, and let's just take the derivative of that. Okay, I mean, it's really amazing. I mean, I even did that. I mean, who would do that, right? Seriously, I mean, I'm really being pedagogical right now. Okay, so all right, just solve for phi 2. Okay, and yeah, I written this because here there is x1 dots, right? And by using that, the original dynamics x1 dot can be substituted by this, by this because this, right? This. Okay, and just solve for phi 2. Okay, this is again, all of those manipulations are simple algebraic manipulations. Okay, here phi 2, right? So using, by the way, using this equality, okay, because we want to phi 2 as a function of x1 and x2, right? Okay, so all of those are x1 and x2, but except z2, right? And let's substitute z2, right, using this expression. And now now we have phi2 as a function of x1 and x2. Okay, and we can make it more explicit by just substituting this term for phi1, right here, just right. Okay, and let's expand that. So now we first determine phi1 of as a function of x1, and then phi2 as a function of x1 and x2. Now we will find u, right, as a function of x1, z1, z2, but by using simple algebraic manipulations we can just recover as a function of x1, x2, and x3. Okay. Okay, so let's check the term 3. This is our v dot expression, and we want this term to be this by manipulating phi1, phi2, and u, right, control law. Okay, and so we managed to find phi1, and as a result of that phi1 dots and phi2 dot now. So now let's make this, right, minus z3, because minus z3 times z3 equals minus z3 square. Okay, so this equality, okay, by using that equality you need to just recover u, right, and here it says phi2 dot, right, and phi2 is a function of x1 and x2. Okay, and so you can just expand it as given, and also x1 dot and x2 dot you can just substitute them by looking at the original problem. Okay, and just recover or isolate u. Okay, and by the way, isolate is a function, matlab function that we will use. Okay, so I use that word consciously, right? Again, by using our original equalities, because this equality is we use to, you know, get from x1, x2, x3 to x1, z2, z3, right? Okay, because there will be a transformation, or there is a transformation that helped us go from space to this space, or dynamics to that dynamics. Okay, all right, so again, just doing some algebraic manipulations. Okay, we just substituted z2, or this term for z2, right, and substituted this term for z3. Okay, and again there is x1 dot and x2 dots, and we can just substitute this term for x1 dot and this term for x2 dot just by here x2 dots and also x1 dots. Okay, okay, so we have u, right, our control algorithm, or control law, control law, right, and we can just expand phi1 and also phi2, right, to really have u of x1, x2, and x3, because this is what we need, right? Okay, for example, if you have, where is it, yeah, if you have this original system and someone gives you u as a x1, z2, and z3, you're like, hey, what is z2, what is z3, just give me this, I want this, right, I want my control law. Okay, and u must be dependent on, or must be a function of, your state variables. I mean, given you are interested in state feedback, right? Output feedback is a whole another subject, right? So don't give me that type of stuff, right? I don't want to know what z2 and z3 is. I want to know explicitly what u is, right? As a function of x1, x2, and x3. Okay. So even in the example problems in really good control books, they just don't. They kind of ignore writing the. Okay. Finally, the control law is this. They forget that. Okay. Let me just delete these stars. Okay. Let's look at this. So substitute explicit forms of phi1, phi2 again, and the partial derivatives of phi2 by using, yeah, this is our origin of, this is the, for example, we first found this, right? Okay, then we determine this, and then just after determining that, it's straightforward to find the partial derivatives, right? And let me just delete those. So we have this, but there are phi2 and partial derivatives and phi1, right? By using what we have found previously, just substitute in that, and as a result of that, we will have incredibly long control law where u is a function of x1, x2, and x3. Okay. Note, this computation is brought to you by MATLAB Symbolic Toolbox. Okay, of course. Right? Alright. By that, I'm not getting any money from MATLAB, so MATLAB, come on. Alright, the answer, as a result of that, the answer, of course, I couldn't write that, like manually, right? I just generated that, the control law, right? And coefs is a good function, right? If you have symbolic expression like u as a function of x1, x2, and x3, just give me. In that, I feel like this is more compact form, more like there is a pattern to it, right? Okay, so let's look at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, like 13 expressions. Wow, it's incredible. Okay, so you have your control algorithm, or I'm sorry, control law, right? Okay, so let's check that. Okay, and the best way to check is simulink, right? I mean, you could write, you could write, by, I guess, by using OD45 or something, right? And because x1 something, x2 something, x3 u, but u is now x1 is a function of x1, x2, x3, so you have an autonomous nonlinear dynamical system, which you can of course simulate by using OD45 in MATLAB script. But yeah, I mean, MATLAB or simulink is more convenient because you can easily, of course everything that you do in simulink you can do in MATLAB. Okay, got it. But it is easier, right? The manipulations that you will, or analysis, way more simpler. Okay, so here this is our plant, and the inputs of the plant, the states x1, x2, x3, and u, right, the input. Okay, and outputs of this block x1 dot, x2 dot, x3 dot, right? And let me write x1, x dot, and just integrate that and get x, so fed back to that location. Okay, let me delete all of them. Okay, so this is x1, I'm sorry, x dot, and this is x. So, and your control law, right? This says control law, right? So you need x1, x2, and x3 to construct u, right? So you have that type of block diagram. Okay, let's look at what is in NL plant block, and this is the problem, right? This is the original problem, the dynamics of the plant. Okay, and the control law block includes this function, and this function is, you know, this really long expression, right? And I just copied and pasted to that function. Okay, all right, and this is our initial condition. Okay, you just can't choose or right, select other initial conditions to test. All right, as you can see, x1, x2, and x3. By the way, which one is x1, x2, x3 is not important to me, right? But they all converge to 0. Let's look at the time scale as well, right? They all converge to 0, and the system is, the closed loop system is stable. We have constructed our control law. U as a function of x1, x2, x3, meaning states, such that the closed loop, when we close the loop, the closed loop dynamics, right, x1, x2, x3 dynamics are stable, meaning x goes to 0 as t goes infinity. Okay, goes infinity. Okay, so yeah, this is MATLAB code for problem 1. As you notice from here, I use MATLAB functions to create that incredibly long u as a function of x1, x2, x3. Okay, so let's try to focus on that. Okay, here, first of all, we will have x1, x2, x3, and u, and I just write real because, I mean, they will be real, right? And if you write that, MATLAB has a tendency to, because being real is an assumption or a constraint, right? And if you don't state that constraint, MATLAB will try to solve a harder problem, a solution that would be valid for more general cases, and we don't need that. Okay, so again, phi1 is a function of x1 and phi2 is a function of x1, x2, right? And z2 and z3. Okay, right. So this is the problem. This is the plant dynamics, right? x1, x2, x3, and u inputs. Okay, so the first comment says substitute phi1 plus z2 for x1, and this is, let me go back, what wasn't, yeah, page number 9. Okay, let me go back a little. Okay, maybe it would be better for me to delete all of them, right? Okay, let's focus on this. This is our problem. Okay, this is our problem, and the first substitution is this, right? And also, I'm looking at this. Yeah, you will have that. You will try to find that. Okay. Okay. So substitute that for x2. Okay. Because you have x1, x2, x3, and then you will have x1, z2, x3, and then you will have okay, x1, z2, z3. Okay, the first transformation is this, right? and you need to find z2 dot. Okay. Okay, this is the first substitution, and by using, by using substitute command of MATLAB, right? This is an expression, right? And substitute this term for x2. Here you have x2. Okay. Okay. And by the way, every time you do something, check by using simulink function. For example, x1 dot is a function of, right, is a function of x1 and x2, or is it, right? So to determine the dependencies, you use simulink, which lists all the variables that this is a function of, right? Okay. Okay, after substitution, x1 dot should be composed of, right, phi1 x1 z2. Okay, right? Okay, so nothing wrong with that. Delete all z2 terms in x1 dot and find phi1 such that x1 dynamics is stable. Okay, you know the term 1, term 2, term 3, where we find the for example, in the end we will have x1 plus z2 dot dot dot, right, and z3, but we called it term 1 and we call it term 2 and we call it term 3 really creatively, and this term only needs to have x1 and phi1, right, and this term 2 needs to have, or this term shouldn't have z3. Okay, so just if you have z2 here, just get that to that parenthesis. Okay, and if you have z3 here, get that to that parenthesis. Okay, just by simple manipulations. Okay. Okay, so delete all z2 terms in x1 dot, and we call it x1 dot, right? This, because if you use this Lyapunov function, v dot of x1 is x1 times x1 dot, right? Okay, and this is x1 dot. Let me get another color. I'm really tired right now. Okay, this is x1 dot, and if you have z2, let's get that to the other parenthesis. Okay, and delete that, right? So find z2 terms and remove them from x1 dot. This is the logic, and it says x1 dot without z2, right? How do you delete z2 terms? By just substituting 0 for z2 terms in your expression, which is called x1 dot. Okay, right? And at the end, the Lyapunov function will look like this. Okay, and arrange this expression in this form. Okay, so that yeah, this is what we have talked about. x1 times term 1, z2 times term 2, and z3 times term 3. Okay, and term 1, term 2, and term 3, they need to satisfy some constraints. Okay, and the constraints are the following, right? And term 1, for example, this is the term 1, shouldn't have z2, z3, dot, dot, dot. When I say dot, 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 I mean z2, z3, and any other z sub I terms. Okay, is the point. And term 2, right? And there is a pattern here. Notice that there is a pattern, right? And term 2, this is term 2, shouldn't have z3 and z4 and etc. Since we are dealing with three-dimensional systems, we can ignore z4. Okay, right? And z2 terms to add to z2 parentheses. Okay. The reason why that the name of that variable is really long, because I wanted to make things clear, right? Okay. So first you have x1 and x1 dot plus z1 and z1 dot plus z2 and z2 dot, right? Okay. And we, right, this is our v. I mean, it's going to, anyway, just look at this, right? Okay. But here, but we want to have x1 term 1 plus z1 term 2 plus z3 term 3. Okay, by just simple manipulations. Okay, so if you have here in x1 dot, if you have z1 term, just carry that to, or rather carry that to this z2 parenthesis. Okay, I'm sorry, I made a mistake. z2, z2, z3, z3. Okay, right? Let me delete that. Let me delete that because I don't want to confuse people, right? x1 dot plus z2. It's really tempting to say z1, by the way. Anyway, z2 dot plus z3 dot, this must be, less than 0, right? Okay. And if you have z2 term here, carry that to that, right? What we called, and that's why we called it, if you have z2 term, carry that to that, meaning z2 terms to add to z2 parentheses. This is called, I call, right, here in this program, z2 parentheses, z2, okay, parentheses. Okay, how would you do that? Oh, anyway, okay, wait a sec. For example, let's think about this. I don't wanna gloss over that. Let's say you have x1 plus phi1 plus z2, right? And you have some z2. How would you get that to here? First of all, let's call it x1 dots, right? And by using substitute here, just substitute z2 equals 0, right? Okay, and then subtract that from x1, your original x1 dots, and you have, what do you have? You have z2. Okay, but you need to put that expression in z2 parentheses, and that's why, you need to actually, naming kind of makes things harder, or is not 100% correct, I guess. Okay, wait, let's move on. Wait a sec. So, yeah. Okay. Now I get it. Okay. You have z2, right? And you need to, since this is like x1, we are dealing with, multiply that with x1. And now you have x1 times z2, right? And since you get this term in z2 parentheses, divide this term to z2. Okay, divide this term, by z2. Okay, and then you can write x1. Okay, so one more time I'm going to explain that. You have x1 plus phi1 plus z2. Okay, let's focus on this simple problem. Let's call it z3. Okay, this is called x1 dot and this is called z2 dot. Okay, we just don't want any z2 term in this x1 in this parenthesis, and we want to have x1 term 1 plus z2 term 2. We need to have that type of form where term 1 doesn't have z2 in it. Okay, how would you, as a human being, how would you do that? You would write, probably, if you like me, you would write something like this. Okay, so now this is okay, but we want to have this, right? So if you have that expression, right, just arrange that such that it is in z2 parentheses. Okay, so let's do that manipulation. z2, right? Here x1, right? x1 plus z3. Let's write the same thing. Okay, so now it's okay. So term 1 is okay. On top of that, the term 2 doesn't have or shouldn't have z3 terms, and we can, if we have other. So let's not focus on that. Okay, just that was a simple example to illustrate the idea, right? Okay, we are just trying to do that operation. Okay, and since we want to make things automatic, right? And the simple things, for human beings can be really hard to, code sometimes. Okay, I guess not sometimes. I guess most of the times. Okay, so that's why we multiply that with x1 and divide by z2. Okay, just taking it to carry that location, and every time you do that, check the dependencies using simvar function. Okay, all right, x1 dot equals this. Okay, choose phi1 such that x1 is stable. Okay, and this is the place where we just, if we have x1 plus phi1, right, dot equate this to x1 or something, right? This is that logic, and to do that, this is that, and equate that to, I call it here minus x1, but you can also equate it to that, and isolate. You can't just say solve, right? You need to say isolate. I don't know why, but this is this is the way I did it, and I did. I mean, this is the state, I guess, best way of doing that. Okay, okay, and isolate phi 1 and write RHS, right hand side, to obtain phi 1. Okay, so here you would just write phi 1 equals, you would just write that, right? Just without even knowing that. And this is how MATLAB does that. Okay, basically. And you will need phi 1 dots, right? Phi 1 dots. And for that you need to take the partial derivative of with respect to x1, right? Because x1 is the only dependency, only variable that phi 1 is dependent on, right? And times x1 dots, okay, and check the dependencies with that function. And phi 1 dot must be must be dependent on x1, x2, okay. And again, this is the typical, right, change of variables equality that we kind of memorize that if we are dealing with backstepping control. And just take the time derivative and isolate z2 dot, okay, to find the dynamics of z2, okay. And I'm looking at this, wait a sec. Okay, now we have this, we just write that, okay. And yeah, substitute this for x3 in, because we want to have, we had x1, x2, x3, and then we had x1, z2, x3, and then we did that. And now we are trying to find, okay, wait a sec, x1, z2, z3. We are trying to find the dynamics of x, or dynamics in these new coordinates, I should say. Okay, okay. So z2 dot, right? Z2 dot here. This is z2. Okay. Again, the same logic, right? Delete all z3 terms in z2 dots and find phi 2 such that z2 dynamics is stable. Okay. And this is a typical, you know, you have z2 plus z3. If you have z2, just carry that to that z3 parenthesis type of operation. Again, the same. First, just substitute 0 for z3, and then find the term that you need to put into that parenthesis, z3 parenthesis, okay. And z3 terms to add to z3 parenthesis. Okay, I am aware of that. It looks complicated. Okay, and again, you need to find phi 2. How do you find phi 2? Right, phi sub 2, right? Again, let me write once again, right? If you have term 1, term 2 plus term 3, just, and there is phi 1 here, equate it to minus x1, and there is phi 2 here, equate it to minus z2, and there will be u here, right? Equate that to minus z3, and first solve that to find phi 1, because there will be phi 1 as well, right? And then solve for phi 2, because there will be phi1 and phi2 and also phi1 dot and phi2 dots, right? And then solve for u and obtain u as a function of x1, x2 and x3. Okay, this is the general idea. Okay, maybe I should make that something like that. Okay, because I didn't want to delete that. So we are trying to find phi2. Okay, we are here in this stage, and then we will find u. Okay. Okay. Phi2 must be must be dependent on x1, x2, phi2. Okay, because remember we were writing phi sub 2 of x1, x2. Okay. Okay. And always check, the dependency using simvar. Okay. And yeah, like we here we found x1, we determined x1 dot. I'm sorry, I'm not, it's like really tired right now for a sec. Phi1 dot, right? After determining phi1, we computed phi1 dot, and now we determine phi2, and we need to determine phi2 dot by using this. Okay, and of course we can employ simplify or expand, right, to make things, if there are some things that some terms they need to cancel each other, if we know that, we can employ that. You do that step by step, right? So, and maybe change some things. For example, I write minus z2, but you could also write minus z2 third power, right? You can also write, you can also manipulate or do some parameter selection. You can consider these as parameters that you have the ability to tune in a way. Okay, again checking the dependencies. Phi2 dot must be dependent on x1, x2 and x3. Okay, this is an observation, and this is typical equality, right, for the transformation. And again taking the time derivative and isolating z3 dot. Okay, find z3 dot expression. Okay, and this is the expression, right? This is the equality, and again checking the dependencies. And now this is where we do this. Okay, right? First we determine phi1, and then we determine phi2, and now we are going to determine u. Okay, by just equating that to minus z3. Again, z3 dot plus z3 terms to add to z3 parenthesis expression. Okay. Okay. And u must be dependent on x1, x2, and u, when we find u, when we isolate u, you will have z2 and z3, right, expressions, and we can just substitute, right? And by the way, recall phi1 is a function of x1 and phi2 is a function of x1 and x2. As a result of that, and you can also check, right, and you can also simplify, and you can just determine u is a function of x1, x2 and x3, and you can just use that. Okay, wow, that was hard, okay, for me at least. All right, so this is MATLAB code output for problem one, right? And what this MATLAB code will give us is that it will give us phi1 and phi1 dot, right, and phi2 as a function of x1 x2, and you can just find phi2 dot, but I couldn't write that because it's too long really. So you can, by using, and since this is a polynomial, by the way, right, we know that you can only use coefs comment if you know your expression is a polynomial of that given variables, right? And this is coefficients and this is terms, right? You can just express that. I guess this is compact. Okay, so wait a sec, and wait a sec, and here this is your input. Again, you can just express your input in that. All right, I wonder if I should stop or continue. I feel like it would be better for me to just finish that. Yeah, okay, let's continue then. All right, and this is contract. This is my example. I just made that, right? Constructed that. This is problem 2. Again, this is dynamics x1, x2, x3, and you have u input. Okay, and find your control law such that the closed loop is asymptotically stable. Okay, and wait a sec. Okay, this is dynamics, right? This is your first variable change. Okay, and by doing the same manipulations, but okay, just I mean the same manipulations, right? All right, obtain z2 dot. All right, let's, nothing wrong with iterating the basic ideas. This is our first dynamics, and we will transform to have x1 z2, and initially we will have x3, and then we will have this. Okay, so from here to here is this part, and from here to here is this part. Okay, okay, here we will just write this here, right? And now look at this. We have the dynamics are written in x1, z2, and x3, right? Okay, so here x1, z2, x3, and in the original dynamics are written in x1, x2, and x3. Okay, and again doing the manipulations, doing that transform, we have the dynamics can be written in x1, z2, and z3. Okay, here this is that the dynamics, the new dynamics, right? And we can just employ this Lyapunov function where it can be, you know, written in that fashion, right? By choosing this simple Lyapunov functions. Okay, again, note more sophisticated functions can also be chosen. All right, we are aware of that. I mean, even with these simple Lyapunov functions, you realize how long the expressions are, right? I mean, seriously, this is like third order, right? Even for this really contract but simple systems, but nonlinear, the control law that you get is extremely long, and I cannot even imagine how longer would it be if you were to use, you know, more complicated Lyapunov functions. Okay, so this is, again, we did the same things, right? It's literally this copy and paste, right? Okay, and just write that, because one good thing about selecting your Lyapunov functions in that given simple quadratic form, you can just write that, and this, look how beautiful it looks like. Look at the pattern. Okay, and just substitute by using your dynamics here. Okay, let me just, maybe it would be better, for example, this term and this term. Okay, again, this term and this term, right? They are same, right? We just substitute that and here this term. Okay. Okay. So let me just, yeah, we want this term to be negative, right? And we want to manipulate this expression, this large expression, such that it is written in x1 times term 1 z omg, okay, z2 and z3. Okay, yeah, it's good that I mistype stuff sometimes, right? And we then get to, you know, correct that and find those mistakes, I guess. Okay, all right. Yeah, from here to here, right, we need to arrange the terms. If there's any, again, term 1 should only have x1 and phi1, and phi1 is a function of x1. Okay, so arrange the terms in that, right? And term 2 shouldn't have z3. Okay, so if there is, just arrange the terms, and there is here, right? And just arrange that, carry that to that part, z3 parentheses we call it, right? Okay, here this is it, and we have z2. Just carry that to that location. Here is x1, right? x1. Okay, and here we have z3, but it shouldn't be in that location. It should, let's carry that to that, and to carry that, just, right? Okay, just simple algebraic manipulation. We just take one term to, and we carry that. Okay, this is just what we did. Okay, all right, find phi1 here. So x1 term 1 plus z2 term 2 plus z3 term 3, right? We have this enough. Okay, and just equate it to minus x1. Just write term 1 equals minus, and come on, minus x1, and here equate it to minus z2. Term 2 equals minus z2. Term 3, of course I'm doing without loss of generator, right? Minus z3. Okay, and first solve for phi1, and then solve for phi2, and then solve for u. Okay, the control law. And again, this is what we are doing basically. Here, this is term 1, and term 1, find term 1 should be equal to minus x1, because if you multiply x1 and minus x1, you would have minus x1 square, and again minus z2 square, and minus z3 square, and we know that it is guaranteed to be negative definite. Okay, so this is what we are doing. Okay, so find phi1 such that this equality holds. Okay, and isolate phi1. Okay, now let's focus on, this is term 2, right? But there is phi1 dot in it, and we know, since we determined now the phi1, we can just find phi1 dots, and it will be a really long expression. Okay, but it is an expression that we know nonetheless. Okay, and just equated that expression to minus z2. Okay, here, this is it, right? We need to make it look like this. Okay, and phi2, right? And this needs to be equal to minus z2, okay, and then just solve for phi 2. You know this, you know this, right? Just solve for phi 2, okay, isolate phi 2, okay. I'm not going to going again detail here, expand, and we determined that previously, and take, I just, who would write that seriously? It's like really explicit steps here, right? And there is x1 dot, but x1 dot I just written again the dynamics, the original dynamics, right? X1 is a function of x1, x2, x3, right? Okay, and so this is what you have, and isolate, and you also have minus z2, right? And isolate phi 2, and you have z2, and by using this equality just find phi 2 only as a function of x1 and x2, and look at this expression is a function of the right hand side is a function of x1, x2. Okay, so let's move on, and here this is the v dot expression. We want this to be minus z3, right? Okay, and just the same expression, isolate u such that this expression is equal to minus z3, okay. So, and there is phi 2 dot, but we know what phi 2 dot, however it will be a really long, we knowing us doesn't mean that it is not long, it is extremely long, okay. And recall it is a simple and contrived example, and that's why you need to be skeptical of the people who talks about backstepping and for some reason forgets to, right, mention about the symbolic toolbox, MATLAB or any other symbolic toolbox, right? You need to use symbolic toolboxes if you need to construct a control law using or employing backstepping control algorithm. Okay, this is important. Okay, so this is phi 2 dot, and here look at how long it is, how long of an expression it is, right? And we are trying to isolate u, okay, and then we are trying to write that, make the right hand side of that equality only depend on x1, x2, and x3, and by using those given equalities, the origin of transformations, and by using the, we will have x1 dot and x2 dot, right? By using the original dynamics, we just substitute, right? And u is this, and recall that we need to substitute the explicit representation of phi 1, phi 2 derivative, right, and partial derivative of phi 2, and here we have phi 2 here, right? So you need to substitute these terms, and this computation is brought to you by MATLAB Symbolic Toolbox, and the answer is this. Okay. Check the result by simulating the closed-loop system in simulink MATLAB. Okay, again this is the dynamics here, u, right? Okay, and this is the control law that we just determine using MATLAB Symbolic Toolbox, and this is our initial condition, right? And here this is the states, and they all go to 0, right? Okay, so this is MATLAB code, and you can find this document. This is docx document, and m file, that will be another m file, and also slx, the simulink file. You can find these three, right, documents in my GitHub page. The link is in the description. Okay, and we only change, I guess, the dynamics. Okay, and for example, this part, right, we could have written that, but this is for example, this is the choice, parameter choice, right, and this is also a choice. For example, we could have written z2, or let me just z2 and minus z2 cube, right? Okay, and this is also a choice, right? Again, we can, by the way, we can, of course, we can write z2 fifth power, etc. Just anything that's in that fashion. Okay, and we just find our u, right? And matlab code output for problem 2 is again phi1 dot, phi2 dots, right, and u, right? Here, this is our control algorithm. Okay, and this is the final example, but it will be really short. Okay, so I just written that to summarize the idea. Okay, this is our problem. Okay, when you have that, just by heart do this change of variables. Okay, and you will have that by manipulating that, and then by using your dynamics, right, you have x1, x2, x3, x1, z2, x3, right, and then x1, z2, z3. Okay, from here to here, right, from here to here, again here to here, right, and from here to here is from here to here. Okay, the basic idea is that, right? So you do that, right? Okay, and that's why I include this docx file in the GitHub folder that hopefully you will click on the link in the description. Okay, and okay, just design process, right? Write that x1 times x1 dot, and x1 here, look by looking at this, right, x1 dot is this here, and z2 dot is this, and z3 dot is this, right? Okay, just if you have z2, just carry that to z2 parentheses, right, and if you have z3, carry that to that z3 parentheses, right, and if you have this, I guess you would call standard form, right, you can wait a sec, you can just say that suppose v1, w1, w2, w3, right, positive functions. So this here, this is right, and this is the expression, and look at this term and this term and this term and this term, right? Okay, so now the problem becomes this, because this implies this. Okay, and the best or easiest positive function is again given in quadratic form. Okay, and so here, and you can just cancel by simple manipulation, right? You have this now, just now you have this, right? Isolate phi1 in the first line. Okay, and find, after finding phi1, find phi2, and then finally find u. Okay, and again phi1 dot will be here. You will need to use, or you will use phi1 dots in constructing phi2. Okay, and this is your original dynamics. Okay, and I'm looking at this, and this is phi1 dots, and when you're done with phi1 dots, you can isolate phi2 and then finally find u. Okay, here isolating phi1, phi2, I'm sorry, phi2, we just isolated phi2, right? And then we need to isolate u, right? Here, look at this expression, and we just isolated u, right? Therefore, the control law u, right, is computed through the algebraic operations, which is significantly simpler than dealing with PDEs. Okay, let me just look at that if we have anything. No, we don't have anything. Okay.